Now we're going to discuss substitution and elimination reactions of alcohols. Unfortunately, alcohols are not suitable substrates for elimination and substitution reactions because if they participate in these reactions, we will generate hydroxide as our leaving group. Hydroxide is a strong base, it's also a strong nucleophile, which means it's not an excellent leaving group. It's not stabilized well enough. What we need to do for these reactions to proceed is convert the hydroxide to a better leaving group. And one way of doing this is protonation. So if we take this tertiary alcohol in the presence of HX, an acid, we can protonate the alcohol species. This protonated form can then release water as a leaving group instead of hydroxide. This would neutralize a positive charge on an oxygen and is energetically favorable. This generates a carbocation, which can then be attacked by our nucleophilic halogen to form an alkyl halide. This is one example of taking a hydroxyl group and making it a better leaving group so we can perform a new reaction. We can also convert alcohols to mesylates or tosylates using tosyl chloride or mesyl chloride and pyridine. These are both excellent leaving groups and can be utilized in substitution or elimination reactions. To refresh, the structure of a tosyl chloride is this toluene group as well as a sulfonyl chloride. Structure of mesyl chloride is this methane group and a sulfonyl chloride. Reaction mechanism for this, the oxygen will attack the electrophilic sulfur, which will break one of these pi bonds. When that pi bond reforms, we will kick off a chloride ion. This will give us this new protonated species, which can be deprotonated by the pyridine that we have, and that will eliminate the positive charge on the oxygen. Now we've got a mesylate in this case, which can undergo a substitution or elimination reaction and generate a mesylate ion as our leaving group. This ion, unlike hydroxide, is very stable because of resonance. We can also convert alcohols to alkyl chlorides using thionyl chloride and pyridine. This will give us an alkyl chloride, which is useful for substitution or elimination. In this example, oxygen again will attack the electrophilic sulfur, breaking a pi bond. When the pi bond reforms, we kick off a chloride ion. So again, we have a protonated species, which in the presence of pyridine can be deprotonated, eliminating the positive charge on the oxygen. Now we have this species, which can be attacked by the chlorine. Even though chloride is not a great nucleophile, it's nucleophilic enough to attack this carbon here and break the carbon-oxygen bond. This is facilitated because when we break this bond, we form a new double bond here and kick off this chloride as well. So we end up generating SO2, which is an excellent leaving group because it's a gas, as well as chloride and our alkyl chloride, which can continue in a new reaction. Finally, we can use phosphorus tribromide to convert an alcohol to an alkyl bromide. In this example, the oxygen will attack our electrophilic phosphorus, kicking off a bromide and generating this charged species. Because this reaction does not have a base like the previous reactions to deprotonate this species, we'll actually have a direct attack by the bromide. It's a much better nucleophile than chloride. This will break the carbon-oxygen bond, eliminating the positive charge on the oxygen. So we generate HOPBr2, which is relatively stable. We've eliminated the positive charge, as well as our alkyl bromide, which can undergo substitution or elimination. To summarize, alcohols are poor substrates for substitution and elimination reactions. They can be protonated under acidic conditions to generate a better leaving group. We can also generate a better leaving group by converting an alcohol to a tosylate or a mesylate. We can convert an alcohol to an alkyl chloride using thionyl chloride, or we can convert an alcohol to an alkyl bromide using phosphorus tribromide.